There is something just very comforting about a traditional physical server room. You can walk in, you hear the fans screaming, you look at the blinking lights on the racks.
Yeah, and you can literally put a heavy steel padlock right on the server cage.
Exactly. It feels secure because, well, you can physically see the perimeter, right? You know exactly where the walls are.
It's tangible. I mean, humans are wired to understand physical security. You point to a steel box and say, my company's database is inside that box.
Right. And if nobody breaks the box, the data is safe.
Yeah.
But then you step into the world of virtualization, and suddenly that physical padlock is practically meaningless.
Oh, completely meaningless. We are looking at an architectural landscape that is entirely invisible.
And there's this massive misconception I see all the time, especially for people just stepping into their first professional IT roles. They think virtual machines are somehow inherently safer just because they're, abstracted from the physical hardware.
Yeah, that assumption is probably the single most dangerous mindset you can bring into a data center today. I mean, the architectural reality is that virtualization doesn't eliminate your security risks.
Right, it actually expands them.
It radically expands your attack surface. You haven't made the server disappear. What you've actually done is insert an entirely new layer of software, the hypervisor, right between the hardware and the operating system.
So every hypervisor, every virtual machine, container, orchestration tool, that's a brand new door for an attacker.
Exactly. And the real shatter point here is that if a hypervisor is compromised at that foundational layer, every single virtual machine running above it falls instantly.
So you basically just added a single point of failure that holds up the entire digital infrastructure.
Right. And if you're stepping into an IT role today, understanding how to defend that shatter point is, well, it's your ultimate survival skill.
And to do that, I mean, we can't just randomly start clicking buttons and configuring firewalls, right?
Sure.
We need a master plan.
You absolutely need a plan, which brings us to governance frameworks.
Now, I know the word framework sounds like dry corporate bureaucracy, but if you think about it like city planning, it actually makes a lot of sense.
Oh, for sure. You need zoning laws and building codes to ensure a whole city doesn't just catch fire all at once.
Exactly. So mechanically speaking, how do frameworks like, say, NIST and ISO actually govern a totally invisible virtual environment?
Well, let's break down the mechanics. Frameworks provide the structure that stops IT teams from, just playing a guessing game with security, like the NIST cybersecurity framework, for instance.
Right. That one forces a sequence, doesn't it?
It does. It breaks down to 5 core functions. So you have identify, protect, detect, respond, and recover.
Notice that identify comes first.
Yeah, and that is crucial in virtualization. It forces IT teams to actually catalog their assets before they do anything else.
Because you can't encrypt or build access controls around a VM if your security team doesn't even know it exists.
Exactly. You map the city before you build the walls. And then you have ISO IS 2701, which takes a slightly different angle.
Yeah, from my reading, ISO focuses heavily on building an information security management system, or an ISMS.
Right, which feels a bit less about the technical knobs and dials.
And more about making sure the humans are actually doing their jobs correctly.
You're hitting on the core tension right there. NIST is your operational playbook, but ISO 27001 is really your audit trail.
So it teaches us that secure virtualization depends on how decisions are documented and reviewed.
Yeah, and improved over time. It basically creates a system of accountability. I mean, if a virtual machine is spun up with open ports, ISO mandates that there's a documented paper trail showing who approved it and why.
It shifts security from being just a technical patch to like a shared organizational responsibility. But, theory is great until you are a junior admin staring at a management console on a Tuesday morning.
Right. How do you translate a massive document like NIST into actual keystrokes?
Exactly. Where do you even start?
That's where the rubber meets the road with the CIS controls, specifically version 8. Think of the CIS controls as your practical, hands-on toolkit.
So they bridge the gap between that high-level governance and daily operations.
Exactly. But they aren't just a random list, right? There is a strict operational logic to them.
Wait, so looking at these CIS controls, Control 4 dictates secure configurations for enterprise assets, which basically means hardening your VM templates.
Spot on. And then Control 8 mandates audit logs to monitor your hypervisor for weird behavior.
But are these sequential? Because if I don't do Control 4, isn't Control 8 just generating a bunch of noise?
Yes, exactly. You can't effectively audit your logs under Control 8 if you haven't first standardized what normal looks like using Control 4.
Oh, it makes total sense.
And honestly, neither of those matter if you aren't strictly following Control 7.5, which is continuous vulnerability management.
The mandate to deploy and manage updates.
Right. I mean, why bother logging an attacker walking through the front door if you left the door wide open by not patching your hypervisor?
Good point. So if you are tracking those specific CIS controls sequentially, you're actively fulfilling the broader goals of NIST.
Exactly. You're executing governance on the ground floor.
Okay, I really love that sequence. Establish the baseline, patch the holes, watch the logs. So now that we have our city planning blueprint, let's pour the foundational concrete.
Let's do it.
Let's look at enterprise hypervisors, starting with VMware, specifically ESXi and vCenter, because vCenter is essentially the central command post.
It really is. If an attacker compromises vCenter, they don't just own one server.
Right. They have total control over the entire virtual landscape.
Total unfettered control. I mean, they can delete workloads, silently copy sensitive databases, or just reroute network traffic.
So to defend this foundation, you have to apply aggressive hardening steps to the ESXi hosts themselves.
Yes. First, you enable UEFI secure boot and TPM attestation.
Okay, I hear TPM attestation tossed around in security briefs all the time. But mechanically, what is actually happening there?
So a TPM, or Trusted Platform Module, is a dedicated cryptographic chip. And attestation is basically a mathematical wax seal on your boot sequence.
A wax seal. Okay, I like that visual.
Yeah, so when the ESXi hypervisor boots up, the TPM measures the core boot files and signs them.
So if an attacker tries to inject a malicious rootkit into the hypervisor before the OS even loads?
The measurements won't match. The TPM sees the wax seal is broken and halts the boot process completely. It prevents that compromised host from joining your secure cluster.
That is brilliant.
Yeah.
And beyond the boot process, we also have to lock down how these virtual machines actually talk to each other.
Right, the network traffic.
Because in a traditional physical network, traffic goes north-south, right?
Yeah.
It travels up out of the server, through a physical firewall, and back down.
But in VMware, you have east-west traffic. This is VM-to-VM communication happening entirely inside the hypervisor's memory.
A traditional perimeter firewall on the edge of your network never even sees it. It's like a burglar who is already inside your house just walking freely between the bedrooms.
Which is why relying solely on perimeter firewalls in a virtualized data center is just a recipe for disaster. This is where NSX micro-segmentation comes into play.
So instead of one giant firewall at the front door, micro-segmentation allows you to wrap a distributed, software-defined firewall around every single virtual machine.
Exactly. So if the HR database gets infected with ransomware, micro-segmentation prevents that malware from moving laterally, east-west.
To infect the finance server right next to it on the same host.
Exactly. It contains the blast radius.
Now let me throw a pushback question your way. Let's say a virtual machine is turned off. It's powered down. Or maybe it's just sitting idle in a backup snapshot from 6 months ago.
Okay, I see where you're going.
The operating system isn't running. If it's offline, isn't it perfectly safe from a network attack?
That is a very common assumption, but it completely ignores the reality of how virtualization works.
Oh, really? How so?
Well, this brings us to one of the most hidden, insidious dangers in IT environments. I'm talking about VM sprawl and offline snapshot files.
VM sprawl. So just losing track of what you have running.
Basically, an abandoned, untracked VM is essentially a zombie target. Yes, it is powered off, but its disk files, the VMDKs, they still exist as raw data on your storage array.
Oh, wait. So if an attacker gains access to the storage layer, they don't even need to boot the machine up.
Nope. They can just copy the disk file and extract your sensitive data completely offline.
Oh, wow. So offline doesn't mean out of reach. It just means it's sitting there completely undefended.
Precisely. And honestly, snapshots are arguably even worse.
How could a snapshot be worse?
Let's say an administrator takes a snapshot of a production server before doing a major upgrade, say a year ago, and then they forget to delete it.
Okay, so that snapshot is a frozen state of the machine from a year ago.
Right. Now, what happens if a junior admin is trying to troubleshoot a problem today, gets confused, and accidentally restores that one-year-old snapshot to production?
Oh, I see the mechanism there. You just instantly overwrote a year's worth of security patches.
Exactly. The machine wakes up thinking it's a year ago, totally vulnerable to modern exploits. You've just reintroduced months-old, unpatched vulnerabilities directly into your live network.
Wow, totally bypassing all your perimeter defenses.
Yes. This is why lifecycle governance, strictly monitoring what you have and aggressively destroying what you no longer need, is absolutely critical.
That is terrifying, but it makes total sense. Now, let's contrast VMware with Microsoft's Hyper-V.
Sure, that's a great pivot.
Because VMware is a bare metal hypervisor, right? It is the bottom layer. But what happens when we flip that?
With Hyper-V, you mean?
Yeah, because Hyper-V runs on top of a massive general-purpose operating system like Windows Server. That architecture has to bring a very specific dependency risk, right?
Oh, it's a massive architectural difference. Hyper-V relies on a parent partition running Windows to manage the hypervisor.
So the dependency trap here is that if the host Windows operating system falls to like a basic phishing attack or an unpatched Windows vulnerability, the hypervisor falls with it.
Exactly. It's a single point of failure that is much larger than a bare metal hypervisor.
So it's double the patching. You're securing the hypervisor, but you're also just securing a standard Windows box that has, what, millions of lines of code?
You are. To mitigate this, you have to lock down that host OS mercilessly. You heavily restrict PowerShell remoting.
Okay, and what about access controls?
You enforce strict Active Directory role-based access control, or RBAC, so only a tiny, dedicated group of admins can even log into the virtualization layer.
And crucially, you utilize shielded VMs. I was reading about shielded VMs. Mechanically, how do they protect the data if the underlying host OS is already compromised?
Well, they use a combination of BitLocker encryption, virtual TPMs, and something called the Host Guardian service.
A virtual TPM, how does that work?
It simulates a physical cryptographic chip in software. It ties the encryption of the virtual machine's disk directly to the verified health of the hypervisor.
Okay, so if a rogue administrator tries to, say, copy the virtual hard drive to a USB stick and boot it on their laptop at home,
the virtual TPM detects that the hardware and host environment have changed, and it flat out refuses to unlock the disk.
that is incredible.
Yeah, it prevents tampering even by the people who hold the administrative keys to the host server.
That is a phenomenal layer of defense in depth. So enterprise tools like VMware and Hyper-V have all these built-in guardrails and host guardian services.
They do, yeah.
But let's push into the open source and orchestration frontier. What happens when teams move to environments like Proxmox, where they basically have to build the guardrails themselves?
Well, that is exactly where the training wheels come off. I mean, Proxmox is incredibly popular in agile startups and production labs because it is powerful and open source.
But there's no enterprise handholding.
None. The security of that environment relies entirely on the administrator's operational discipline.
So where do people usually mess this up when they install it for the first time?
The most common failure point is treating Proxmox like an appliance rather than a Linux server.
Because underneath the hood, Proxmox is just Debian Linux. Right.
Exactly. People install it and immediately start spinning up VMs without hardening that underlying Linux host.
Oh, so they leave all the default Linux vulnerabilities wide open.
Right. You must strictly restrict SSH access using key-based authentication, never use passwords, and you could never, ever expose the Proxmox web UI to the open internet.
That seems like common sense, but I'm sure it happens. And what about when you are deploying containers within Proxmox?
You have to understand the difference between privileged and unprivileged LXC containers.
Break that down for me. What is the difference mechanically?
So, a privileged container runs with root user lights that map directly to the root user of the host machine.
Uh-oh. So if an attacker breaks out of a privileged container...
They are root on the host. Game over.
Wow. And unprivileged.
An unprivileged container uses user namespace mapping. Even if the container thinks it's running as root, the host machine sees it as a restricted, unprivileged user.
Okay, so it maintains deep isolation from the host kernel.
Exactly. It is a much safer way to operate.
Which is actually the perfect pivot to talk more broadly about containers, like Docker and Kubernetes.
Yeah.
Because I've always heard this analogy. If a virtual machine is a heavy, slow-moving cargo ship carrying an entire operating system, a container is a fast, lightweight speedboat.
Right, I've heard that one too. But that analogy always feels incomplete to me.
Oh, why is it incomplete?
Because it leaves out the mechanism of why they are fast. If a virtual machine is a cargo ship, it has its own engine, its own crew, and its own navigation.
Meaning its own independent operating system.
Right. A container is a speedboat, but it doesn't have its own engine. It relies entirely on the doc's engine, the host machine's OS kernel, to run.
Ah, I see. That makes them incredibly fast to spin up, but it also introduces a massive shared risk.
Precisely. If that doc's engine gets compromised, all the speedboats sink instantly.
And when we talk about compromising the dock, I've heard horror stories about the Docker daemon socket, which usually lives at varendocker.sock, right?
Yes, the infamous Docker socket.
So if I'm understanding this mechanism correctly, if a container can somehow talk to that daemon socket, it's basically like a prisoner getting their hands on the warden's walkie-talkie.
That is a brutal way to picture it, but it is entirely accurate.
Because they can just order the prison to open all the doors. Am I close?
You're spot on. The daemon socket is the API interface that listens for commands and tells Docker what to do.
So if you accidentally expose that socket to a container or expose it over a network port without authentication,
You have effectively handed over root-level access to the host machine. The attacker can use that walkie-talkie to order Docker to spin up a new privileged container, mount the host's entire root file system into it, and take total control.
that is wild. Does that actually happen in the real world?
Oh, all the time. A few years ago, there was a massive wave of automated attacks doing exactly this.
Really? How did that work?
Attackers built bots that just scan the internet for exposed Docker daemon sockets. Within minutes of a socket touching the public internet, the bots would use the API to spin up hidden containers.
What were they doing? Stealing data.
Mostly, they were designed exclusively to mine cryptocurrency. They would completely chew through the host's CPU and cost organizations thousands of dollars in compute fees.
So how do you take the walkie-talkie away?
You advocate for rootless container runtimes, like Podman, which just don't require a central root daemon to function. Or you configure Docker itself to run in rootless mode.
Okay, and what about permissions?
You intentionally drop unnecessary Linux capabilities. That way the container only has the exact permissions it needs to run its specific application and absolutely nothing more.
Makes sense. But when you have thousands of these speedboats, you need a harbor master. That's Kubernetes.
Kubernetes orchestrates it all, but securing it requires massive discipline. You have to isolate workloads using namespaces.
And enforce strict role-based access control, right?
Yes, so developers can only touch their specific namespaces. And you need runtime monitoring tools like Falco.
What does Falco do exactly?
Falco sits there watching system calls for anomalies. Like, say, a web container suddenly trying to access a sensitive system password file it has no business touching.
Which brings us to how we actually build all of this infrastructure today. Infrastructure as code or IAC, tools like Terraform?
Right, IAC is everywhere now.
Here's my thought on this. If IAC is like a factory mold stamping out infrastructure perfectly every single time, a flaw in the mold means you just automated your own security breach at a massive scale.
That is the double-edged sword of automation, absolutely. If you write an ISC template that leaves a firewall port open and you deploy it, you don't just have one vulnerable server.
You instantly have 500 servers with an open port.
Exactly. Misconfigurations propagate at the speed of code.
So how do you govern code that builds physical reality?
You have to treat it like highly sensitive software. You store all your ISC in version-controlled Git repositories.
And you never, ever hard code secrets.
Right.
Like passwords or API keys.
Never. You use dedicated secret managers like HashiCorp Vault to inject those at runtime. And you utilize drift detection tools.
Oh, I think I get this. So drift detection is basically a security alarm for human error.
Pretty much, yeah.
So if I'm troubleshooting and I manually log into a server and open a port to test something, but I forget to close it, the drift detection tool flags that reality has drifted away from the secure blueprint in our codebase.
That is exactly how it works. It ensures that the secure code you wrote is actually the reality running in production.
Okay, so we've secured the local hardware, we've secured the containers, we are scanning our code.
Yep, a lot of ground covered.
But what happens when this entire infrastructure isn't even in our building? What happens when it's hosted on someone else's servers in the cloud, AWS and Microsoft Azure?
The cloud. A whole different beast.
Let me play devil's advocate here. If my company pays AWS millions of dollars a year, why am I still responsible if we get hacked? Shouldn't they be handling the security?
That is a fundamental misunderstanding of the shared responsibility model. Think of the cloud provider like a landlord, and your company is the tenant leasing an apartment.
Oh, me? I like that analogy.
The landlord, so AWS or Azure, is fully responsible for the physical security of the building. They secure the massive data centers, the physical servers, the biometric locks on the doors, and the underlying hypervisor.
But as the tenant?
You are 100% responsible for what goes on inside your specific apartment. You are responsible for your data, your network routing, and your identities.
So if I leave my apartment door wide open and my TV gets stolen, that's on me, not the landlord.
Precisely. And the data backs this up. Misconfigurations by the customer, not provider hardware failures, are the leading cause of cloud breaches by a massive margin.
So what does leaving the door open look like mechanically in the cloud? Because in a traditional network, the firewall is the perimeter. But in the cloud, I always hear that identity is the firewall.
Because identity is the only perimeter you have left. Let's look at AWS, for example.
What are the biggest risks there?
The biggest risks we see are over-permissive IAM roles. Administrators will use a wildcard, an asterisk, in a permission policy because it's just easier to grant a script access to everything rather than figuring out exactly what specific database it needs to read.
Oh yeah, the classic wildcard lazy fix.
Exactly. We also see dormant root accounts left unsecured, and famously, Amazon S3 storage buckets.
Right, the open S3 buckets.
Yeah. An engineer will back up a sensitive database to an S3 bucket, accidentally toggle the permissions to public, and within seconds, automated internet scanners will find it and download the contents.
And over in Azure?
Similar story, different terminology. In Azure, the risk often comes from assigning the owner or contributor roles far too broadly across a subscription. We also see teams failing to secure service principals.
I hear service principal tossed around all the time in Azure documentation. Mechanically, what is that? Is it just a bot account?
Essentially, yes. It is a non-human identity created for an application or a script to authenticate and access resources.
And what makes them so dangerous?
The danger is that service principals don't use multi-factor authentication. They use secret keys or certificates.
So if an attacker steals a service principal's key from an insecure code repository,
they can automate data exfiltration at lightning speed, completely bypassing human MFA checks.
Wow. So what does this all mean for the professional listening right now who is stepping into this environment? What is the mandate?
The mandate is that security vigilance is a shared professional responsibility across the entire IT team. It doesn't matter if you are a developer, a sysadmin, or a network engineer.
Everyone owns a piece of the puzzle.
You must enforce multi-factor authentication everywhere. You must utilize least privilege religiously. And you must centralize your logging.
Using tools like AWS CloudTrail or Azure Defender for Cloud.
Right, so you can actually see when someone is rattling the digital doorknobs of your environment.
Okay, let's take a breath and recap this journey. We started at the physical foundation, looking at how to govern and harden bare metal hypervisors like ESXi and Hyper-V using NIST and CIS controls.
We covered a lot.
We explored the mechanisms behind the dangers of abandoned virtual machines and the do-it-yourself discipline required for open-source platforms like Proxmox.
Yep. And the shared kernel risks of Docker and Kubernetes.
Right. And the double-edged sword of infrastructure as code. And finally, unpack the shared responsibility model of cloud giants like AWS and Azure.
And the common thread through all of it is operational discipline. Cybersecurity in virtualization is not a product you buy and plug in.
It is an ongoing practice of taking professional ownership of your attack surface.
Exactly.
Before we go, I want to ask you for one final thought, something drawing from the very bleeding edge of the source material that our listeners can take away and mull over.
If you want to look at the bleeding edge, look at cognitive platforms as a service, or CogPOS, and AI infrastructure.
Okay, tell me more about that.
Well, we've spent this entire discussion talking about securing infrastructure as code, right? Securing the logic, the configurations, and the identities.
Yep.
But as AI models are integrated deeply into our environments, the data those models ingest dictates the decisions they make. So the question becomes, how do you secure the cognitive layer?
Securing the cognitive layer, that is a wild concept.
Think about the mechanism. If an attacker doesn't bother breaking into your server, but instead subtly poisons the training data of an internal business AI model, your infrastructure might be perfectly intact.
Oh, wow.
Your firewalls are up, your IAM roles are tight, your hypervisors are patched, but the logic running the business is now compromised. How do you govern a system that is constantly learning and changing its own behavior based on the data it eats?
Wow. That completely redefines the perimeter again. It's like we're back at that physical server room we talked about at the very beginning.
Full circle.
You can put a heavy padlock on the door to protect the physical servers, but if the AI inside those servers has already been fed lies, the padlock doesn't matter at all. The call is coming from inside the house.
Exactly. The frontier of security is moving from protecting the hardware to protecting the data to protecting the cognition itself.
That is a phenomenal thought to end on. To you, the listener, thank you for diving deep with us today. Look at your own virtual environments this week with fresh eyes. Check your IAM roles, track down those zombie VMs, and start asking the hard questions about what happens when your infrastructure starts thinking for itself. Catch you on the next deep dive.